Hi, and welcome to the third week of the Extreme Value Theory course. In this video, what we're going to be looking at is the content introduced in Chapter 4 of the lecture notes, which looks at how we can extend our modelling approaches to deal with non-identically distributed processes. So what are the aims of this chapter? Up until now, we've been focusing really heavily on modelling the extremes of independent and identically distributed random variables. What we want to do is look at relaxing the second part of this assumption that the marginal distribution of each random variable is the same. Next week, we'll come back and look at the first part of this assumption that each of the observations are independent. One approach to tackling this modelling problem might be to consider particular marginal distributions for each of the random variables x1, x2, and so on, and then use these marginal distributions to derive asymptotic properties for the partial maxima in exactly the same way that we have done for IID random variables. This approach isn't that great in practice because you usually don't know going into things what your marginal distributions are going to be, and so you can't rely on a particular set of asymptotic properties that you've derived. What we're going to do instead is look at techniques from generalized linear modeling and from time series modeling to come up with two generalizations of the frameworks that we've already developed that can handle these non-identically distributed random variables. So before we go on to do that, let's just take a minute to think about some different ways in which processes can have non-identical marginal distributions but still have independent terms. So let's consider a few ways that we could construct such a process. We start off with an IID set of random variables, zt. We could add some sort of trend in their mean by simply adding a function of time to the value of each of these random variables. We could consider a trend in their variance by multiplying each of them by a function of time, which here we're going to call beta of t. And you should note here that if the zt have non-zero mean, this is also going to result in a trend in the mean. What we can do is combine these two to get both a trend in mean and a trend in variance by first multiplying the zt process by a function of time and then adding on a secondary function of time. We're not necessarily limited to the first two moments of the distribution that are changing over time in this type of model. What we can do is allow the shape of the distribution to change over time using this function lambda of t and applying a Box-Cox transformation to our sequence of IID random variables. In all of these transformations, it's not necessarily time that's going to be driving the non-identical distribution of the process. So we can generalize this to allow our functions alpha, beta, and lambda to not be functions of time specifically, but of one or more covariates, which we're going to describe by the vector x of t. So if we have a process with independent but not identically distributed terms, how can we go about modeling the large values of that process? The first method we're going to look at borrows from generalized linear modeling and considers letting the extreme value model parameters to be functions of some set of covariates. What this allows us to do is to continue using all of the methodology that was spent the last 2 weeks developing. So we can use block maxima, R-largest, or peaks over threshold approaches, and we simply let the parameters in whichever of these models we're choosing to use be defined as some function of available covariates. This is exactly the same idea as in GLMs, for example, when you have a Poisson random variable and you allow the rate to depend on the length of a roll of cloth, say. One thing to note is that the extreme value distributions that we're using aren't members of the exponential family. And what that means is that we can't use techniques such as iteratively reweighted least squares to fit these models. What is available to us, however, is direct maximization of the likelihood or log likelihood function in order to estimate our model parameters, and all of the available techniques that usually surround that. So if we're comparing nested models, we can use likelihood ratio tests to do so. And if we're trying to construct a model with lots of covariates, we can use forward and backward selection to determine which of these should be included. Just as with generalized linear models, some of our parameters need to take values in specific ranges. For example, the scale parameter in either the GPD or the GEV models need to take positive values, and the threshold exceedance probability in the GPD model needs to take a value between 0 and 1. We can ensure that these hold in exactly the same way as you've seen in other courses by using a link function. So if we have a GPD model, for example, and we're wanting to model the conditional exceedances of some high threshold U, what we can do is model those as a generalized Pareto distribution, allowing our scale parameter sigma to vary as a function of covariates. And because it's difficult to estimate, we're going to keep the shape parameter psi constant. In order to ensure that our scale parameter takes positive values, what we can do is model the log of its value as being some linear combination of regression coefficients and covariate values. If we take the exponent of both sides here, we see that this is going to ensure that our sigma u takes positive values for any value of the coefficients or the covariate values. The threshold exceedance probability can be modeled in much the same way, but using a logit transformation to ensure that it falls between 0 and 1. Now that we're considering adding in covariates to our model, we can extend the idea of return levels that we met earlier. The idea of a conditional return level is to work in exactly the same way as our marginal return level that we introduced in previous weeks, but now it's going to be for a particular value of the covariates. So in particular, the 1/p conditional return level at time t is going to be described by the value y subscript tp, and it's going to be the value that is exceeded with probability p given the particular covariate values. The way that we work out this conditional return level value is exactly the same way as for our marginal return level, but this time we're not rearranging the CDF of y of t. Instead, we're rearranging the conditional CDF given the covariate values. So for example, if we're looking at a GPD model and we're looking at a conditional return level that is bigger than our modeling threshold, and our probability of exceeding the threshold at that time is greater than our return probability, then what we get is a very similar expression to what we had before, but now each of our parameters depends on the covariate values at that time t. If we want to take this and recover the marginal return level, so the return level not conditional on the covariate values, then what we have to do is find the expectation of this expression over the joint distribution of the covariate values, which we're going to denote by pi. Apart from in really rare cases, you're not going to know the joint probability distribution of those covariates. And so when we're trying to calculate this expectation, we're not going to know the distribution function pi of x. One way around this is that we can simply approximate this by its empirical distribution. So look at this expectation over the observed values of covariates. What this means in general is that you're going to have to use a numerical solver to find the yp value that satisfies this equation. So what we've seen there is a way of extending our existing modeling techniques to account for non-identical margins. This second technique lends from time series modeling, and the idea is kind of the opposite. What we're going to do is take our process which has non-identical margins and try and transform that back to have identical margins so that we can use all of our existing methodology as is. In order to do this, what we have to do is assume some particular form for the departure from identical margins. So for example, we might assume that there is a mean trend. So our observed process y of t is some IID process zt plus some function of time alpha. What we then do is estimate this structure component to get an estimate alpha hat, and then remove that structure from the process through a series of transformations. So in this case, we're just going to subtract off the estimated mean trend. What this gives us is a transformed set of observations, z hat of t, and we can use all of our existing methodology to fit a method model to those transformed observations. Once we've done that, we can then back transform our results about z hat of t onto the original y scale. So for example, if we'd estimated a conditional return level, z hat pt, and we wanted to translate that onto the y scale, we'd simply have to add on our estimated mean trend at time t. This idea isn't restricted to just looking at simple transformations such as mean trend. If we've got enough data, we can look at a very general model in this case. So here what we could consider is a form where we have a trend in the mean, the variance, and the shape of the distribution. What we do is estimate each of these three functions, alpha, beta, and lambda, and then construct our estimated process, z hat of t, to model using our IID methods. Generally, when we're estimating these functions, we're not going to recover them perfectly. And so it's a good idea to try and mop up some of the residual non-identical distribution by combining this with the approach that we saw before. So because our process z hat of t won't quite have identical margins, we can model it where our extreme value parameters still depend on covariance as well. When combined, these two techniques give you a really powerful way for modeling non-identically distributed data. And the bulk of our concentration is going to be on the first method, because the implementation of the second can get a little bit intense. So that's everything I had to cover in this video. I hope you enjoyed seeing how we can extend the range of models that we can represent in extreme value theory, and I look forward to seeing you in the examples class on Friday. Thank you.